Good afternoon and good morning to some of you. I'm so happy to be invited to this international workshop from waste to advanced material and product. For the next 45 minutes, I will talk on the topic that I have selected: recent development in biocomposite research in Malaysia. The lecture outline, I will talk on the biocomposites in Malaysia, and I also will talk on the institution where I'm working, and also some institution in Malaysia related to biocomposite in brief. And I will share on the recent research of our research group that include the product development that we develop, design, and fabricated. And I will share some of our recent publication. Okay, University Putra Malaysia, formerly known as University Pertanian Malaysia or University of Agriculture Malaysia, is recognized by the Independent Government Assessment as one of the Malaysia's leading research university, offering undergraduate and postgraduate courses with a focus on agricultural science and its related field. UPM is an institution that has become a glorious legacy to the history of agricultural education in our country. UPM's agriculture goes through education and research, producing quality human capital and enriching knowledge, exploring various innovation and creating an excellent life. Okay, our ranking is 132 in the world. And now I'm focusing on the institute that I'm working called INTROP. It is a Institute of Tropical Forestry and Forest Product, UPM. It is one of the higher institutions, center of excellence at the national level on tropical woods and fiber. We are focusing on biocomposite, biopolymer, and the research field related to that. Okay, another institution that are working on biocomposite is Fiber Research Institute of Malaysia, or FRIM, but it's focused on wood composite. Now, I will review some of the recent work on biocomposite in Malaysia. Research on biocomposite in Malaysia initially and mainly focusing on characterization of natural fiber polymer composite, where polymers were from synthetic polymers. In the recent years, research on bio-based polymer is intensified. So in addition to working with synthetic polymer, we are working bio-based polymer. And okay, this is one thing that our research group have done. This is on the work on the design, mainly conceptual design, method selection, and product development, and including life cycle analysis. There's one question to Dr. Mariam earlier. We have done some work on life cycle analysis. But for the natural fiber, we mainly focus on tropical fibers. This is some data of the mechanical properties of selected natural fiber. Now, I would like to focus on KENAF. Yeah? The strength is 295 megapascal, and we don't have the data for modulus in this chart. And for oil palm, mainly empty fruit bunch, the strength is 248 megapascal, and the tensile modulus 3.2 gigapascal. And another important fiber that our research group is working on, the sugar palm. I think this plant is not known to many people, but this is our main strength. And it has quite good tensile strength, which is 421.4 megapascal and 10.4 gigapascal. I will go into detail in these three main fibers that you are working for the biocomposite. Now I want to explain to you on the main fibers that I use in Malaysia. And I have done some work using the oil palm, or the scientific name Elaeaceus guineensis. On the left-hand side is the plant, and on the right-hand side, the top, it is the empty fruit bunch, mainly for oil, palm oil production, but waste or the residue byproduct from the oil palm plant, you can see there it is in the form of fibers. Okay, let I explain briefly on the history of oil palm or palm oil. In our country, the first plantation were mostly established and operated by British plantation owners, such as Sam Darby and Bosted, and remain listed in London until Malaysian government engineered their Malaysianization throughout the 1960s to 1970s. Okay, the latest information about this product is that in last year, Malaysia accounted for 25.8% and 34.3% of world palm oil production and export, respectively. Meaning, significant amount of the production of palm oil in the world. So Malaysia accounted for 9.1% and 19.7% of the world total production and export of oil and fat in the same year. Therefore, what I can conclude, we have abundant resources of oil palm waste and residue, mainly in the form of fiber that our research group, have or will, make full utilization of that. Okay, this chart show the biomass in general, oil palm biomass, meaning that from the oil palm frond, for instance, so we can have product, but for the fresh fruit bunch, is the main product. We can make a palm kernel cake, or you can get shell, which is 5.5%. Empty fruit bunch, it is a waste, but we make use of that, full use of that, and it is 20%, 22%, and the fiber is 13.5%. So obviously, from the palm kernel cake, from those we can make a oil, but also people use it for home effluents. And in this, I can conclude that 10% goes to oil, but 90% is biomass. Okay, we focus on the fiber alone. So look at the plant. We see that oil palm fronds produce oil palm frond fiber, which is 70%, and the empty fruit bunch, we have from that empty fruit bunch fiber, which is 10%, and oil palm trunk. We can get the oil palm trunk fiber, which is 5%. Okay. The oil palm fiber are used as reinforcement and fillers in composite, in biocomposite. They are used with the thermoplastic, mainly and thermoset, including biopolymer. This composite has wide application in furniture and automotive component. And Malaysia Palm Oil Board, MPOB, has developed series of technologies on manufacturing thermoformables plastic composite through compression or extrusion process for car components such as bumpers, trimmings, rear parcel shell, spare wheel cover, and splash shell, and also plastic pallet. Okay, now I will explain on the research work that we have carried out using oil palm fiber. It is quite recent. The grant was provided by Sam Darby. It is a quite a famous company, so they provide us some money. In that, we are working on developing the safety helmet through a holistic integration of practice, ergonomic, and engineering among oil palm plantation harvester. This is the title. So meaning that this project, is a huge, the it's not just focusing on natural fiber composite, but it is beyond that, which is working on the ergonomics and other aspect design. But at the end, one of the product is the biocomposite safety helmet. So there are 4 objectives of the work. So that is related to this lecture is the development of a sustainable material to improve nearly proposed customized safety helmet. The journey of making a safety helmet for agriculture. It is none in the world, so we try to develop the safety helmet for plantation workers to protect at least the head and body. Empty oil palm fruit bunch fiber composite is very promising material to be commercialized, especially for low-cost product. The product, the fiber itself, is not capable of producing, very high, impact product and high structural product. But for the cost product, it has been implemented. Low cost means cheap raw materials, require less energy to fabricate, and the most important is the material are environmentally friendly. Okay, looks on the pictures on the left hand. A picture on the left hand side, the workers, they are taking the branch, from the plant. So look at the head and the body; they are being exposed. That's why the motivation here is to wear a hard hat. The bunch is quite big, huge, and the head is small. But at least there is some protection. Otherwise, all this while there is no such thing. Safety device or safety things, that safety equipment being implemented. So this is one of the effort that our research group have done, and luckily we have got the funding from Sandabi, and they won that. As shown on the right hand side, that the plantation workers should have some kind of protection through the safety helmet. So one of the product that we are thinking is on using the fiber from the oil palm fiber itself, on the oil palm plant itself. Okay, we have done a series of design to improve because it's a new product, so to develop the new design for the plantation workers. So group of designers, the sit down together, come up with a concept of the helmet, and through some prototype and a model 3D model and solid modeling. Okay, we have done some publication work. Mainly, we start with the hand layup. Hand layup. I think this is quite simple process, but I think to start with, to produce the prototype, we managed to produce 20-30 helmet from the oil palm. But I just want to emphasize here, this is only at the developmental stage. We produce the helmet, and we also take care of the aesthetic value, the finishing, the painting, also being taken care. And this is some of the effort for improving the product. We do some kind of testing, fitting all the accessories on the helmet. Okay, this is what that we hope from the project, that one day SAMDABI will implement in each and every workers that are working in the plant. We can use this in Malaysia, in our neighboring country, in Indonesia. But I just want to highlight here, we have not, this product has not been used yet, but it has been submitted as the final product was launched by our former Prime Minister, in one of the event. Okay, to me, this is some new things that we have done for benefit of the peoples. Okay, the next the fibers that we are focusing on is a kenaf, hibiscus cannabinus. So I think some of you have seen the plant. So from that we can produce the fiber. I just want to do some introduction on kenaf industry in Malaysia. Kenaf was introduced in Malaysia in early 1970s and was recognized as a potential alternative fibers material for the pulp, paper, and wood composite industries in the late 1990s under the 7 Malaysian Plan 1996 and to 2000. Compared with other plants, the yield of kenaf are relatively higher, up to 25 tons per hectare, thus presenting more economic advantages. For the past several years, kenaf fiber have been shown to be suitable for composite applications such as particle board, MDF, wood plastic composite, non-woven material, and pultruded product. The characteristics of kenaf fiber are similar to those of wood compared to like hemp, flax, and jute fiber. They have got similar properties. So according to research result, the kenaf yield 12 to 13 tons per hectare is greater than those hemp, flax, jute, thus providing a more cost-effective raw materials. It was reported under the Malaysian climate, yield of kenaf vary from 2 to 25 tons per hectare. This is the board, the agencies that are dealing with kenaf, National Kenaf and Tobacco Board Malaysia. And this agency was actually meant to replace the tobacco slowly, but that's why the name of kenaf and tobacco is included together. We have done quite a number of work on kenaf. So we published work with CRC Press 3 years ago on kenaf and fiber and composite. And if you can see here, kenaf comprise the bars and core. Okay, both bars and core can be used for biocomposite. And I want to share some of the properties of kenaf and non-wood fibers. So kenaf bars, the tensile, I think I have mentioned earlier, 295 to even can go up to 1,191 megapascal in terms of strength, and the modulus can go up to 60 pascal. So they are quite comparable with the other important fibers like hemp, jute, flax, and sisals. And also I include the oil palm, which is our main product as well, as comparison. Okay, I just want to share one of the recent research work on kenaf. It is for the defense industry, and we have the hybridization of Kevlar and kenaf fiber reinforced epoxy composite for ballistic protection. So our colleague at UPM, they are working on the armor protection like on the left hand side, but my research group, we focus on the work on spall liner for military vehicles. So to develop or to study the use of the kenaf in hybridization with Kevlar for the spall liner, one of the important component in a tank. So the work was done in collaboration with Science and Technology Research Institute for Defense Malaysia under MINDEF. So we want to produce this. I mean, the synthetic. There is a potential to reduce the synthetic fiber, and by replacing it partially with kenaf fiber to make hybrid composite. Okay. Now this is the spall liner that I mentioned. Spall liner are composite panel which made with a synthetic fiber mainly, mounted to the inside of the shell structure of armored vehicles. They protect personnel inside by catching small fragments of the outer shell blown into the vehicles by the concussion of incoming ordnance before it contact them. Used alone or in combination with metal or ceramic, spall liners help increase crew survivability in combat. So you can see that the picture at the bottom there, which spall liner and without spall liner, there are some safety issue with spall liner can be solved, it can be minimized. And in market, for the spall liner, they made using the woven glass fiber and also polyethylene and polypropylene with aramide fiber. This is what are the product in the market. So we try to replace or at least to incorporate to hybridize with the Knauf fiber. At least some green material will be inside that vehicles. Okay, the left hand side is all Knauf, and B is the hybrid of Knauf and Kevlar. The left hand side is all Kevlar, and then B is the Knauf and Kevlar hybrid. C also hybrid but different arrangement. D also still again a hybrid, and E is all Knauf. So what we did was to check which one is the best, to investigate which combination is the best. Of course, Knauf, all Kevlar is the best one. I think this is quite common sense. But we want to see, what is the contribution of Knauf there. Knauf and Kevlar fabric were hand laid up with the epoxy matrix by mixing epoxy and amine hardener in the ratio of 2:1, and 2 thick mild steel plate were used as mold. This is quite simple. This is the outcome, or the material that we use, woven Knauf. And woven Knauf, by the way, is not easy to get. Not many company are producing that. Mainly we can get it Knauf in the form of non-woven, and Kevlar on the right hand side. So we try to hybridize them. The photo below are the hybrid laminated composite after ballistic test. Okay, we carried out quasi-static punch shear test to study the penetration resistance of composite in terms of static load. It focused on penetration process, penetration resistance, energy absorption, and also the failure of hybrid laminate composite. In this study, an experiment was carried out to understand the penetration behavior of Knauf Kevlar hybrid laminated composite under quasi-static. So this is one of the tests that we carried out. And on the left-hand side is schematic of quasi-static punch shear test, fixtures and conical shape penetrator used in this study. And also, one of the important tests that we carried out is the ballistic impact test. Ballistic impact experiment we conducted on this material, Knauf and Kevlar hybrids, to determine the ballistic limit and any energy absorption. So we have the facilities at our lab in our university, and in one of the lab in our university. So we carried out that test. The left-hand side is the actual setup for ballistic test, and B is schematic test setup based on NIJ standard. And the standard, that is used for the test, ballistic impact test. The ballistic test was conducted an indoor firing range of 9 millimeters, 8 gram bullet, which propel at the target using a powder gun approximately following the standard for ballistic test for armor. And this is some of the result that we get in terms of ballistic limit, and also the result as we compare to the material, all Kevlar up to all Knauf. So we can see all Knauf has got the lowest value. Hybrid B and C, D recorded lower than Kevlar epoxy composite 9, 16, and 39 respectively. The difference in ballistic limit in hybrid composite, which consisted of the same number of Kevlar fiber, denote that the negative effect of non-woven Knauf hybridization with the Kevlar fabric. So we can see that with Knauf the value is reduced, and this is the picture of penetration damage behavior of surfaces, rear and front and cross section of the sample, and damage surface of composite after ballistic test. So from this study, you want to see where the Knauf can contribute in terms of ballistic study in the defense industry. So with this, we managed to publish going to be published a book called Composite Solution for the Ballistic, which include the work on the use of Knauf and natural fiber composite in ballistic application. Okay, this is one of the product that we develop and we in fact commercialize that successfully and become very popular among the many people. They like to buy as a gift, funded by our bursar of UPM, a frame from Kena fiber composite. This may look simple, but this is well received by the society. So we have good, packaging. We have, frame that they can use. They when this one they know that this is from green material, they are so happy. And this is the process that we perform on. To make the composite, we have started with Kena core fiber. We mix with the high density polyethylene and to become a biocomposite. Okay, the publication is quite simple using the injection molding. We have biocomposite there, comprise high density polyethylene, and we put in the hoppers in the injection molding, and we make into the Putra frame after some assembly. This is how the assembly process took place. We have also some logo of our university there and have good packaging. It was successfully commercialized and was launched in 2007-18 by our minister, our former Minister of Agriculture. Okay. The next source of fiber that I want to focus is on the sugar palm. I think many people, they are not familiar with this. This is called Aringa Pinata Urema. So this is the plant, and people say it's useless. People misuse this plant. They just burn it down there. But our research group managed to get the fiber and to have a good fiber, extract the fiber, and we managed to make use of the fiber. Okay, the property of sugar palm fiber, we have the on the left hand side, the tensile modulus 5.9, tensile strength 2.76. To me, that is quite good because this plant, the fiber from this plant has been used in the past, like in the Sultanate of Malacca. They used this as make a small boat. Even during the time of the British in Malaysia, they used this as in the ship cordage. So meaning that this fiber has got a very good quality, and for instance, the durability, the longer you soak inside the water, the better the properties. It's quite, amazing. So that's why we believe that, this plant has got so much potential, and we managed to publish with the CRC Press books dedicated to that fiber and form biopolymer from sugar palm plant. Okay, one of the product recently that we developed is solar panel from sugar palm. We want to develop this product further. So this is the fabricated solar module. A is a module with well exposed to sun radiation. B, front view of the modules. C is back view of the module showing the seal back sheet. So this is one of the recent product that we made from the sugar palm fiber biocomposite as part of the component in the solar panels. And we have protected this through IP, and we have the company next week try to commercialize this product. Okay. This is the schematic diagram of the proposed solar modules, including utilized component and public functional part. We can see that there are tempered glass, encapsulant film, solar cell, encapsulant film again. And then this is where the biocomposite from sugar palm is included. PVDF is one of the advanced polymer, and short sugar palm fiber composite that are included in between. Okay, we published the work on the physical properties and mechanical properties of this product, and I think I will read some of the result or some of the activities that we carried out. For instance, this work is to prepare, to produce, and to investigate mechanical, nanomechanical, and physical properties of PVDF reinforced with a short sugar palm fiber composite. And we use the melt mixing approach and hot and cold press molding. And we carried out the study of the mechanical testing and also physical testing, density, water absorption, moisture content, and thickness swelling. And mechanical property of this material display good flexural and tensile enhancement. And the use of sugar palm fiber led to the adequate interfacial bonding between fiber and matrix. The composite exhibited outstanding physical property and excellent resistance to water absorption, moisture content, and thickness swelling. Okay, this is another result that we get from the study on the thermal and optical and technical properties, they are quite good. The optical property of the PB exit are critical component, and they are good in terms of resolvent and transmission. And also we carried out the development process itself. We published in this work. Okay, now again with the sugar palm fiber, we work some on the hybridization with the glass fiber with Proton. I think Proton is a national car of Malaysia, to produce the product component called anti-roll bar. So these are the component that we are try to replace. We have get help, technical help from Proton. They give us some like drawing and give some advice how to produce. Well, I think it's quite big challenging because as we know that sugar palm is not that strong, and the mechanical performance is not that good. So our research group was entrusted to carry out the conceptual design, and also just prior to pre-publication work, we work on the identification of customer, of environment, and then we work on the material selection, and also the conceptual design and manufacturing process selection. So these are the mainly our activity, but we have also our colleague on also working on the development and publication. So we carry out the idea generation, concept development, and concept selection. So the point that I want to make here is that the work on conceptual design of biocomposite is very limited. So we are the team in the world that are focusing on the biocomposite conceptual design, material selection, and life cycle analysis, and also like concurrent engineering of that biocomposite. I think for those who are in design, you are familiar with this one, with the functional specification, force identification, material selection, for product development. So we carried out the design process using some established method, and these are the concepts that we come up for the anti-roll bar using sugar palm fiber composite. So our colleague, the other group, they developed the hybrid glass and sugar palm fiber and to make anti-roll bar, and using the VRTM manufacturing process. So anti-roll bar prototype has been developed. So we have have some ongoing project in Proton. Okay, another work is on the nanocellulose. So it's not my main area, but because we want to focus more on sugar palm. As we know that sugar palm fiber, we work with the starch fiber, biopolymer. It's done by our research group until we come up with the nano stage, nanocrystalline, nanofibrillated. Some of our co-workers are working on that. And this paper is on the development of and characterization of sugar palm nanocrystalline, the nanocellulose starch biocomposite. And this is how the fiber, the nanocellulose was produced. It's also how the starch was produced. It is quite not easy job. We have to climb the tree and get the starch, and we do some processing to develop the fiber at the end. And using the right plasticizer, we got the nanocellulose using the solution casting method, the nanocellulose biocomposite. This is some of the SEM result of the sugar palm bleach and sugar palm cellulose, and at the end, sugar palm nanocellulose. This is some result when we increase the amount of the biopolymer starch, so the tensile strength to be improved, but the modulus in this case they are tend to reduce. And the recent work we want to use for bio-based packaging, so we incorporate the cinnamon essential oil. Yeah, this is a quite new work, and we carry out the antibacterial activities on mechanical properties and tensile, the physical properties, and to see what is the potential from this 100% sugar palm product with the cinnamon essential oil to become the bio-based packaging. This is ongoing work, and we have few PhD students working on that. And this is one of the transparent film from the sugar palm, nanocellulose sugar palm starch biocomposite, and the density when we include the cinnamon essential oil, they tend to decrease. But the tensile strength there is not much different in terms of the strength properties. And okay, I think the final project that I want to share with you on this, during the pandemic, the COVID-19 pandemic, we got some budget from the Ministry of Higher Education to work on sustainable green technology by way of transforming disinfected COVID-19 non-woven polypropylene waste into briquette char, biopolymer char through polymer composite through a pyrolysis system. We are given only 6 months to do this. The PP are the major composition in manufacturing of COVID-19 isolation gown used by healthcare workers, where the low technology, low temperature, this waste PP sample were pyrolyzed and turned into solid char with long isothermal residence time in batch reactor. The yielded char were then characterized and optimized, and the optimum one is used for fabrication of char sugar palm starch composite. The mechanical, mainly the compressive strength and thermal property of char composite with the weight ratio were prepared, and the main result in increasing the starch, the biopolymer content, enhance the compressive strength of the composite, yet reducing the high, but have got reduced high heating value. So we found that 80-20 weight ratio is proposed to be utilized in fuel and barbecue coal application, meaning that in terms of compressive strength, adding the biopolymer is a positive move. That's why we believe that biocomposite can contribute during the COVID-19. This is the objective. I think I have explained it a bit earlier. So from healthcare center, we got the gown and we pulverize it. We make into waste powder using the process flow pyrolysis. We got the char and we add the sugar palm starch. And then we got char sugar palm starch composite and can be used in many applications like in barbecue, fertilizer, and water treatment. And this is again how we have developed the composite. And this is the gown that we wash them properly, so that there is no, they can be disinfected. We collect and washing the PPE and do the pyrolysis process. And see, from non-woven polypropylene PPE, we get the powder, and we do some testing and thermal decomposition of propylene through the slow pyrolysis, and then finally, we got our product, and I think this is a very good work because the government is interested in that. We're going to submit the final report to the ministry, and they're going to be in part of the policy making exercise by the government through the input that we got. It's like a handpicked project. They asked us specifically to work in the short time for this product. So this is what I said. The strength is good when you add more the biopolymer, and also the heating value also not so bad. It's still good when you add biopolymer, meaning that biopolymer has got so much contribution to this during COVID-19 biopolymer composite. So we can conclude from this that char reinforced sugar palm starch with about 30% sugar palm starch content is, you can see, the most optimum, the best suitable for fuel application due to its enhanced compressive strength, as well as high combustibility, enough combustibility to produce better coal product from plastic waste. Okay, I just want to share some of the publication. Maybe some of you can take advantage of this. We can read that we are quite active in writing books. As I said, the composite, we are working with the design of biopolymer composite material using concurrent engineering approach, advanced processing properties and application of starch and other polymer. And we're also working with the natural fiber composite in terms of concurrent design and material selection and work, and also tropical natural fiber. As I said in the beginning, we are focused on tropical natural fiber composite. And the application of natural fiber composite can be used in biomedical that we published last year, and also the natural fiber composite from the vinyl ester and vinyl polymer also, very important. The contribution of natural fiber is very important in this study. And also, as we understand that the biocomposite can be used in the car, and the recent book that was published last week on bio-based packaging, a lot of contribution from biocomposite in packaging, and we also published one on manufacturing of natural fiber composite, and we work on also green composite. And the recent work on specifically on the Roselle fiber composite is published in academic press on the biocomposite, particularly the fiber are taken from the Roselle. And we're also working with the lignocellulose for bioeconomy, future bioeconomy, and the circular economy. And also, this is recent work designed for sustainability. Is we focus on green material, particularly biocomposite, looking at the design aspect in terms of how we handle the environmental issue and sustainability issue. And we're also working with the mineral fillers composite, which is part of them are biopolymer, natural fiber. And this 100% natural fiber biocomposite from the plant, 100%. We publish also. We also use it in drilling process, hole making, and also we have done some work on neural network related to biocomposite, and where natural fiber composite also included. Okay, I would like to invite you to come to our conference on the 5th Wood and Fiber International Conference 2021 will be held on 16 and 17 November. I'm the chairman for this. I think you can visit our website, so you can have the mutual discussion and share our knowledge and expertise in this area. Okay, I would like to conclude my talk. Research work on biocomposite is limited, really, and biocomposite is another emerging composite research. Our natural fiber resources are still underutilized. There's a lot of scope to work on. High impact biocomposite research and industrial and community services are equally important. And finally, I would like to thank Professor Raoul and Mr. Ibo for invitation for this very important workshop. And also the Fibrenamics. And also I would like to thank my university, University Putra Malaysia, for research support. With that, I would like to conclude my lecture. Thank you so much.
Sapuan, thank you very much for your presentation. Very interesting. You've shown lots of applications of agro waste and natural fibers. We have some time now for questions. If participants want to put some questions and have the possibility to interact with Sapuan. We have one question here, Sapuan. So from Zunjarao Campbell, nice presentation. Do you think that the natural fiber reinforced composites will create a great load on agricultural land use?
Okay,
and
thank
what
you.
should be the approach of reusing waste materials? You can unshare your presentation
the natural fiber
if you want.
composite. Yeah.
You don't need to share the presentation
natural
now.
fiber composite
just to have your face with us.
Great load on agricultural land. Okay. This one here, we can be selective.
Okay, if not, no problem.
We don't have to use all the agricultural, product for our biocomposite. Oh, sorry.
You have that stop sharing there.
Yeah. Okay. Now, the issue is that we say that the biocomposite will utilize the land. So to me, I don't believe that, because we have so many, as I emphasized many times, that abundance resources, and I don't believe that, because we have so many, as I emphasized many times, that abundance resources, and many of the fiber are still not underutilized. You take the example of the banana stem. We got so many banana plants being produced. They get the fruits, but the stem are wasted, so they're being thrown. So this can be utilized to make the product, to make the fiber and product. And the one those used for food production, they let them use for that. But there are waste, a lot of waste that we can use for biocomposite. Okay, this is very interesting question when we try to put forward this problem, to solve the problem in our industries. This is one of famous question. But as far as the economic aspect is concerned, you know that biocomposite are waste. Natural fiber are waste. So in terms of material cost, we save a lot on that as compared to glass fiber or carbon fiber. Okay, this is one thing for sure. And I would say that the biopolymer, if you want to use, biopolymer can be cheap if you get the polymer from, starch, which is starch available commercially. Okay, the biopolymer that is available commercially, like PLA, of course, that's very expensive. But you can just buy in the flour, like sugar palm flour is available. You can go to Shopee, you can get. And then from this is quite cheap. And then we can get abundant, huge amount of biopolymer that you can use with the natural fiber. So, and of course, the only problem is the application. It is not, for structural application. It's for mundane application. Oh, surface modification. Okay, this is quite important, because why? The treatment of the surface is quite important because, as you know, that the hydrophilicity and hydrophilic nature of the natural fiber, they are, the bonding is always giving you problem because of that. The properties tend to be, you got low properties, in terms of tensile strength, tensile modulus. So a lot of work on how to, treat the fiber with the alkaline treatment, with even in sugar palm that I mentioned, you can soak in the water. The longer you soak inside the water, seawater, the quality will improve. You see, I would say PLA is the best, of course, but the price is quite expensive, which is biopolymer, right? I think everybody agreed that one, understood that one. But for cost-wise, as I mentioned again, you should work on the starch. You can get it for cheap. Put a plasticizer, you can get. This is the potential. Look at what are your application and how much cost. What is the cost limit that you have? Taking this into consideration, yes. I read one article. They make PLA with a natural fiber for structural component. Yeah, of course the price is a bit high. And even at the moment, we are working with a Steelcase. Steelcase is one furniture company in US, but they have branch in Malaysia. They give some money. So we try to use Kena as well as PLA for their chair, and the executive chair. So this is how we can get the benefit from that. I think, Prof, you are correctly pointed out that. But despite that, I pointed out during my lecture that as you increase the amount of kenaf with Kevlar, you hybridize that, the property is getting, lower and lower in terms of strength, for example. This is indication it's not good. But we have to tolerate to some extent. As far as the standard or test specimen allow, so we can try to reduce the. They allow to reduce for instance, the strength. We can use the natural fiber because they have different role. For example, cost. Yeah, the carbon footprints reduction. Improvement and other thing, helping the poor so that creating the job. So there is another work from our colleague using the coconut coir, as well as part of the coconut plant. They have tested, against standard that they are okay in terms of performance, but not as the best ideal as like Kevlar. But still, they can help. Yesterday, our commodity minister, declared that Kenaf, like we have IBS, industrial building system, they call it Kenaf building system. This is being announced. They get a lot of budget in our country on using the Kenaf building system, meaning that all the product are made from Kenaf composite and to produce house. And we have done a lot of work on building performance. Again, as I would like to emphasize, in for example, in building, we have a lot of like woods, right? So you will know that the kenaf is like similar to wood. Yeah. So any part that can be used from wood, kenaf can replace that. Yeah. So meaning that is the huge application really. I think this is very good move because I think silk, because this is as awesome, silk is very expensive. I think we have colleagues who working with silk. In some country they can get it quite cheap. I do not know. So, but yes, certainly this is a good move really to work with the hybrid of silk and Kevlar. As far as I said, as far as you don't exceed the limit, I mean the strength, for example, not become too weak, so you can use. And also the bioresin, I would suggest now, as I mentioned many times, that PLA is the best candidate. PLA, I read one paper, I think from Spain, they use for bus, component from PLA and also from the natural fiber. We are yet to try. We have the project with the steel case for the chair, executive chair. Yeah, I think I would say PLA the best. I showed to you just now, we published one book on material selection of natural fiber composite. It was published by the Elsevier. You can read my book, and we have done a lot of work on that. In addition to that, we have done recently, that book was published in 2017. We have students working on PhD, we published in high impact journal using the selection of biomaterial for food packaging. One PhD student just graduated. For even we use a lot of method. See, in our research group, I think not many people are doing it. I think we are the only, group in the world. We are working on selection of, using various method like ANN, artificial neural network, even to the extent students use the statistical method. The student, the best background is statistic. They work with the natural method selection for biopolymer. And say, you can always visit my book, and also you can always in contact, and I can help you a lot. Yeah. Yeah. So happy that you invited me. Thank you so much.